Good morning, friends. Okay, last lecture we have seen the T section numerical on the bending stresses. Today we will going on the next section. This section is given rectangular section. Again, you have given the inside that particular rectangle is given. Okay, first you have to check the given figure is symmetric or not about the x-axis section. Okay, check that this dimension is given is total 100 mm by 150 mm is given. Okay, 100 by 150 mm outside rectangle, and inside rectangle dimension is given 50 by 75 mm. 75 mm. If you have taken the axis, the center, then check that above and below you will get the same image or not. If we have taken here the section, then we don't get the above because here is a 25 and here is a 50. If you have taken on the y-axis, then you will get the mirror image, but not for the x-axis. We require for the x-axis. That's why first we want to calculate the position of the neutral axis. You know how to calculate. Okay, another thing is given. You have given the cantilever beam having a UDL 2 kN per meter and total span is given 3 meter. And same thing is given for the simply supported beam. At that time, we want to calculate maximum tensile as well as compressive stress induced in the given object. Okay, then how to find out the maximum tensile stress as well as compressive stress? Okay, this figure is not symmetric, that's why we want to here parallel axis theorem. You know that what is the parallel axis theorem? Last lecture we have seen. And because we want that, I will calculate here m value for the cantilever and as well as simply supported beam. Okay, what is the maximum bending moment? M is equal to W square by 2 is there. Okay, last lecture also we have seen, and second unit also we have seen that thing. WL square by 2. This is the maximum bending moment. What is the W? Check that W is given 2 kilonewton is there. Meter, I will take as it is, and this 3 meter is there. Square divided by 2. You will get how much? 9 is there. 9 kilonewton meter is there. You can convert this 9 into Newton per mm. Newton mm. How to convert this? Kilo means 10 raised to 3. Again 1 meter is equal to 1000 mm. Then again you will get the 10 raised to 3. Means total 10 raised to 6 Newton mm. Okay. Then second one for the simply supported beam. Where we will get the maximum bending moment? Yes, M is equal to what? Yes, correct. M is equal to WL square by 8. What is the value of W? Again same, 2 into 3 square divided by 8 is there. If you are solving this, then you will get the 2.25 kilonewton meter is there. Again you have to convert into the what? 2.25 into 10 raised to 6 Newton mm. Why Newton mm? Because another value will get in mm. This value is given in mm. Okay, all of you getting how to calculate this? You know the standard condition. This total span is given L and UDL is at W kilonewton per meter. At that time you will get the WL square by 2 is the moment. Okay, then next one, take that. Next one we want to calculate the position of neutral axis. It is denoted by the NA. How to calculate the position of neutral axis? We know that y bar is equal to, say, A1 y1. Okay, last lecture we have plus. Suppose this is the first component outside rectangle and this is the second component. We want to this smaller component minus from the bigger component. Okay, then you will get the y bar neutral axis position. A1 sorry A2 y2 divided by A1 minus A2. That's it. Okay, remember that if you have given any hollow component inside that bigger component, then you have to minus and calculate the position of the neutral axis. Last lecture we have start from the bottom. Okay, but in this lecture I will tell you how to solve from the top. Okay, you will get the same answer. Don't think about that. See, y bar is equal to what is the area one? What is the area of the outside rectangle or bigger rectangle? Is 100 by 150 is there. 100 by 150. 100 into 150. How to calculate the y1 value? Check that. This total depth is given 150. 150 divided by 2. And where we will get the y1? Suppose here this. Suppose here you will get the y1. I will draw here y1. Okay. Then minus what is the area 2? What is the area of the small rectangle? This 50 by 75. 50 by 75. Okay. Then next, what is the y2? What is the y2? We'll start from the top. This 25 is given. Y2 is related to the. You have to calculate the centroid of that small rectangle. Where is the centroid? 75 by 2 and plus this 25 distance. Means we are finding from the top. We are finding from the top. Then you will get the y2. What is the value of y2? This you will get the y1. Then what is the value of y2? Check that. Area 2 is there, y2 is there. 25 plus 75 by 2. Okay, 75 by 2. This will get suppose here this one is y2. This plus this one. Okay, then you will get this value y2. Then next one, area 1 by area 2. Area 1 is again 100 into 150. Minus what is the area 2? 50 into 75. Then what is the y bar top? I will write here at the bottom y bar top. You will get the, if you are solving, then you will get the 79.60 mm. Okay, where is this 79? This one coming. Suppose here is the neutral axis. You have to show in the figure this two value. This is the y bar top. Okay, this one how much? 79.16. Then how to calculate the y bar bottom? If you have start from the bottom, then you will get this value, right? We are starting from the top, that's why you will get the y bar top. How to calculate the y bar bottom? Yes, anybody? Y bar bottom. Check the total depth of given component is 150 minus this y bar top. You will get the y bar bottom value 16. This value you will get the near about 70.83 mm. Okay, once you have got the y bar top and y bar bottom, then write in that figure bottom 70.83 mm is there. Okay. Then next one, check that. Next one, we want to calculate what? We want to calculate the moment of inertia about the neutral axis. We know the bending formula, right? Moment of inertia about neutral axis. Okay, and how to calculate that? Again, we want the here two components, consider one and second one. Ixx is equal to, you will get the formula Ixx1 minus Ixx2. We want to the minus that smaller component from bigger component. Then you will get the moment of inertia about the neutral axis. Then what is the value of Ixx? I will directly put here value. Ixx1 means what? This is not symmetrical figure. That's why you have to use here parallel axis theorem. BD cube divided by 12 plus AH square is there, right? AH square is there. BD cube divided by 12 plus AH square minus this for 1 and this is for the second small BD cube divided by 12 plus AH square. Okay, this is given for the second. Okay, then we will calculate. I will put the value in that equation. Check that equation. Yes, you have to put this value. What is the B? Check that. B of this bigger component. B is 100 and B is 150. Means is equal to, I will put 100 into 150 cube divided by 12. Okay, check that. Then plus what is the area? Again same 100 into 150. Okay, what is the h square? H square means what? Last lecture we have seen y bar minus what? Y1. Y bar minus what? Y1. What is the h square? Y bar minus Y1. What is the Y bar top? We have considered the top. Right? 79.6 minus what is the Y1 value? Already we have calculated that Y1 value is 75 bracket square. This is for the first minus. What is the minus? Again second part area, check that. This 50 into 75. Sorry, 50 into 75 cube is there divided by 12 plus again area 50 into 75. Yes, into what is the h square for that second component? What is the h square? Y bar minus y2. Y bar minus y2. What is the y bar top? 79.16 minus what is this value? Y2 value I think 37.5 plus this 25 is there, na? You will get I think 60. Yes, how much you will get that value? 62.5. 62.5 bracket square. This is for second. Then you will get the Ixx is equal to, what is the value of Ixx? Get that 25.80 58 into 10 raised to 6 and then raised to 4. This you will get the Ixx value. Okay, check all of you, do the calculations. Okay, then we know the bending formula, right? We want to calculate the bending stress, sigma T and sigma C. Bending formula. What is the bending formula? Yes, m by I is equal to what? Sigma by y. We want to calculate the sigma. Yes, to calculate that sigma, m by I is equal to sigma by y. I will write here for the sigma T. Check that. Sigma T is equal to tension. First we want to decide for which beam you have to calculate. First I will take the cantilever beam. Okay, first condition is cantilever beam. We want to use the formula related to the cantilever beam. Okay. Then sigma T is there. Sigma T is equal to, you will get the m by I into yt. Why yt? Okay, we have seen the bending nature. We have seen the bending nature for the cantilever beam. Right? What is the bending nature for the cantilever beam? I will draw here. Check that. This is the bending stress distribution diagram. Here you will get the sigma T above the neutral axis, and below the neutral axis you will get the sigma C. And what is this distance? This distance is a yt is there. And where is the yc? Below the neutral axis. Below the neutral axis. Then you have to put the value in that equation. We want to calculate sigma t is equal to, what is the m value? M we have calculated here, m is equal to 9 into 10 raised to 6. 9 into 10 raised to 6 Newton mm. What is the value of Ixx? 25.58 into 10 raised to 6, right, into Yt. What is the value of Yt? Then check that. And what is the value of Yc? Yt means y, this portion, above the neutral axis. 79.16 is there. 16 is there. Then you will get the Yt is equal to what? If you have calculated this sigma t is equal to, then you will get this 27.85. Check that. This is in Newton per mm square or MPa. Okay. Similar way, you have to calculate the sigma c value. How to calculate that? We know the general formula, m by I is equal to sigma by y. Then sigma c is equal to, again you will get the m by I into only yc will be changed. Okay, and put the value in that equation. What is this value? M is again same, 9 into 10 raised to 6. This 25.58 into 10 raised to 6. 10 raised to 6 get cancelled into, what is the value of yc? This value below the neutral axis, 70.83. 70.83. Then you will get sigma c is equal to, check that again, 70.83. You will get, if you have calculated, then 24.92 Newton per mm square. Sigma c is equal to. Okay, you will get the first answer for the cantilever beam. Similar way, you have to calculate the value of sigma t and sigma c for the simply supported beam. Okay, then how to calculate that for the simply supported beam? I will check that. This is a simply supported beam. Yes, all of you getting? Yes, good. Then simply supported beam, SSB, I will write. Simply supported beam, you know that generalized formula, m by I is equal to sigma by y. For the simply supported beam, what is the nature of bending stress distribution diagram? We have seen above the neutral axis, you will get which value? Yes, sigma c is there, and below the neutral axis you will get the sigma t is there. With the above the neutral axis, again you will get this distance is a yc, and below the neutral axis you will get the yt. Reverse of the cantilever beam. Okay, then first we will calculate the sigma c. Sigma c is equal to, you will get the m by I into yc. Okay, what is the m? Again we have calculated the m value, 2.25 into 10 raised to 6. 2.25 into 10 raised to 6. What is the I? I is constant. This I value is constant. We are getting that value. What is the Ixx value? 25.58 into 10 raised to 6 into 10 raised to 6 into, what is the yc? Check that. Where is the yc in that figure? Check that. Here is yc. Compression will get above the neutral axis for the simply supported beam. That's why 79.16. Then you will get the sigma c value. What is this value? If you have calculated, then you will get the 6.96 Newton per mm square. And what is the value of sigma t? Sigma t is equal to m by I into yt is there. Okay, m and I value is same for all, 10 raised to 6 divided by 25.58 into 10 raised to 6 into, what is the value of yt? Below the neutral axis, means y bar bottom, 70.83. Okay, then what is the value of sigma t? If you have calculated, then you will get the 6.23 Newton per mm square. Yes, this is the answer. Okay. Guys, don't confuse. You have to remember, only check that which type of object is given. If you have given the symmetric object, then directly divided by 2. Okay, this that divided by 2, you will get the y bar value. But if you have given the y bar, if you have given the unsymmetric component, then you have to calculate the y bar is equal to area 1 into y1 plus area 2 into y2 divided by a1 plus a2. If you have given the 3 component, then again there is a area 3 is added and y3 is added. But if you have given the hollow portion, then you have to minus. You have to minus. Okay. Then you have to remember the bending stress distribution diagram as per the nature. If you have given the cantilever beam, then see, if you have given the cantilever beam above the neutral axis, you will get the which value? Sigma t value, and below the neutral axis you will get the sigma c value. And if you have given the simply supported beam, reverse of that, this value you will get. Okay. And also you have to remember the standard condition. What is the standard condition for the cantilever beam? The beam is having a UDL, okay, W, and this span is given here. Then you have to know this WL square by 2. There will get the maximum bending moment. Okay, there will get the shear force 0 and we will get the maximum bending moment. And second one, where we will get the maximum bending moment in simply supported beam for same condition, WL square by 8. Okay, if you know this, then you have to use the generalized formula, put the value and calculate the answer. Very simple. Okay, today we'll stop here. I have completed all type of the numerical on the bending stress. Okay, next lecture we will start the shear stress distribution diagram, how to draw the shear stress distribution diagram, how to find out the shear stress. Okay, all these things we will see in the next lecture. Thank you.